This video, we're going to show you some of the example related to the drag force, which is special cases, the air resistance, and also some of the example of the circular motion. During the lecture, we talk about the drag force, which you might have a smaller object or you might have a larger object, and their drag force is the resistance force, which is similar to the friction force. It depends on some coefficient, and also some will be depends on the velocity. The coefficient depends on the type of the object, the shape, so all the other things that is not included. So based on that, you can see the majority of this property is really just depends on the speed of the object. So the force is always opposite to the direction of the motion, and how much that is depends on the velocity. We're going to look at one special case over here, and it's also carry an important idea called terminal velocity. So what is a terminal velocity? The terminal velocity simply means when you have the case where the net force is equal to 0, your velocity will not change. Remember, when we talk about the Newton's first law, there's two conditions will satisfy with the first law, which is either at a rest or moving at a constant speed or constant velocity. And that is the terminal velocity. Terminal velocity is going to be a constant velocity. It never change. When velocity never change, that means you should have a net force equal to 0. Okay, so that's the important concept behind this. Now, when you are using the parachute, and this is actually a terminology we use in the parachuting, when you jump out of an airplane and you open the parachute, what happened just during the process is when you jump out of an airplane, you are doing a free fall, right? You start with a 0 velocity, then you are going to gain the velocity as you approaching to the ground. And that's simply because the acceleration, which is our g, that is 9.8, every 1 second, you're going to increase 9.8 amount of the speed, which is a meter per second. Every 1 second you are going to gain that much of the speed. You can think about about like a 10, right? The 9.8 is about 10. So the first second you gain 10, the second second you gain another 10, and so on and so forth. So if you go up, like approaching to the ground, your speed will be very fast. And to save you, that we use parachute. The purpose of the parachute is to give you another force. That force is to moving you up, just like when you're doing the lab, that we have a tension. The tension force lifts the object, but the object is attracted by the earth. So that force is the resistance force. And it's similar to your friction case. When you push to the right, the friction try to prevent it from to the right. Okay, so as you can see over here that we have two pictures. On the left represent the situation where you just start jumping out of the airplane. You just start beginning to open the parachute. Now, or you didn't open the parachute. Even though you didn't open the parachute, you yourself also have a certain situation to create an air resistance, right? You're going to feel that. If you are against a fan, you're going to feel the resistance. That is the same resistance they were talking about here. But that resistance is very small compared to the gravitational force pulling downwards. And therefore, you can see the blue line represent the air resistance. If you didn't open a parachute, yourself has a very small area, and that is like a small object, so the resistance is small. However, the gravitational force is way larger than the air resistance. Therefore, the red color represents the gravitational is longer than the blue one. And because the net force along that direction is not equal, the red one certainly is longer than the blue one. You have a net force, and the net force should go downwards. So that's why you keep on accelerating downwards. It is not a free fall because we put air resistance into consideration. That means you are not moving as faster as you are in vacuum. When you are in vacuum, you don't have the air, therefore you don't have air resistance. What we are more interested is on the situation at the right-hand side. What happens if you open the parachute? When you open the parachute, because you increase the area that you can have the air resistance, and the drag force, which is the resistance, depends on what? This drag force depends on the C and V square. And it's at the opposite direction, so sometimes we put the negative sign over here. This negative sign simply means is opposite to the direction of the motion. C is a constant, and the V is the speed. Oh, which is this one here. Now let's use the D here to represent the drag force. And if that is the case, then that means these two has to be equal, right? So how do we make it equal? Because I have a force going this direction. This is your F of drag force. This one here is your weight. And that has to be equal, simply meaning your F of D, and that is the CV square. I didn't put a negative because if I make it go up to be the positive, then this will be a positive number now. And your W is going downwards, so I'm going to minus W. That has to be equal to 0. Because that is the case, your net force equal to 0. And you're going to have a constant velocity motion. This constant velocity is what we call the terminal velocity, and we try to find this. Okay, so that's very simple. You write this equation, and instantly you can say the CV squared is equal to W, and W is equal to M times G, and let's look at what information that you have. We have 70 kilogram, which is the mass. What is the G? Well, 9.81 meter per second square. And what about the C? Well, C is given over here. This is the C value, 18.0 meter per kg per meter. And then you can solve for the V. So the V squared is equal to 70 kilogram times 9.81 meter per second square divided by 18.0 kg per meter. Okay, that's 0.0. And be careful when you do the calculation, always think about the sig figs. These all have 3 sig figs. When you do a multiplication or division, and you take the minimum number of the sig figs, and which in this case is 3, so we're going to take 3 sig figs, and you can do the calculation on this case. Let me just quickly punch the number. 70 multiplied with 9.81 divided by 18, I got 38.15. And that should give you a meter square and second square, but then you have to take the square root of that. So the velocity of that will be 38.15 meter square second square. That gives you square root of that. And you only take 3 sig figs, so that would be 6.18 meter per second. So that's so this problem carry like 2 information that you need to know. How do you calculate the drag force based on the velocity? and you have to know what the constant is. The second important concept about this is, what is the situation you're going to have the terminal velocity? All right, without knowing that, then you won't know what equation that you should use. Let's look at the second example over here. The second example is about the circular motion. We're looking at a circular motion that's going vertically. And this is the Ferris wheel. Then you have, when you sit on the Ferris wheel, if that go around with like a circular motion, do you feel the same way when you're on the top or you are at the bottom? Or when you are ascending or you descending, are you going to feel the same way? And we can actually do a calculation to find out what happened to that situation. As you can see that we make a picture on the right hand side, and is the person that's sitting in the chair of the Ferris wheel. What you feel when you are in that wheel, and what you feel is the feeling from the seat to push you. Okay, certainly you are attracted by the earth, but what you feel is actually the reaction force. Your butt is going to feel that chair pushing on you. So it's probably not very obvious, but this is how you actually feel. Now, if you understand that this is going to be how you feel, then we wanted to know this end, which is the chair pushing on you. If the number of the end is different, that means you feel differently. And how much difference can we, just using some kind of equation or idea that we learn in the class, and to figure out that? Now let me describe the problem that's given. So you have this wheel and they give you the R. This R represents the radius of the circular motion. The V represents the velocity, and the magnitude is the same, meaning when you're on the top or any place along the circle, the magnitude, the length is the same. However, the direction is different. The direction keep on changing. When we talk about circular motion, the circular motion is going to give you an acceleration. That acceleration is simply just due to the change of direction. That acceleration is what we call the centripetal acceleration. Sometimes we call radial acceleration. So this A sub cent is equal to this, a V squared over R, where V is the speed. Okay, we don't look at the direction. Direction is determined by another thing. The R represents the radius, how big the circle that is, and that is determined by the R. The direction is always toward to the center. It's toward to the center of the circle. Okay, now to understand this, you have to make a free body diagram. So let's look at a free body diagram. If we look at the top, so let's say this is the situation at the top. When you're at the top, because you have a mass, so you're going to give the chair a force where the force is going to be m times g. This is the weight. And you are going to also experience a normal force from the chair because you are sitting on the chair. So the chair is going to give you a force. This is the normal force. Okay, so, and what is the result of this? The result is that you're moving along a circle and the speed is the same, but direction keep on changing. That result is going to give you a force. That force is called the centripetal force. That force is a center-seeking force. The force is always toward to the center of the circle. And what is the centripetal force? This force cent is equal to the mass times your acceleration of the centripetal. And that is also equal to m times v squared over r. Because we know the a is proportional to the v squared, inverse proportional to the r. So that is what happened in this case. Okay, and what is the direction of the force? The direction of force is toward to the center. So let's look at the situation that we have over here. If you look at you at the top, now you have a way going down. This is the way. You have a normal force going up. This is the normal force top. And what is the result of the centripetal force? Centripetal force is going toward to the center, so this result force is toward to the center. When you write this equation, in this case, the equation of motion is going to be like this. The net force in this direction, if I make this one to be, let's make a toward to the center to be the positive, so opposite to that. This is at the top. The net force will be equal to m times a cent. Okay. And what's the net force? And going toward to the center to be positive. Well, that's going to be the W minus your N at the top. And that's equal to your mass times this acceleration, where this acceleration is the V squared over R. If I reorganize this one, I just wanted to know how I feel. Again, this is how you feel when you sit on the chair. How you feel is the normal force coming from the coming from the chair. That equal to W minus N V squared over R. What is W? W is M times G. So M, you can factor out the M. That will be mg minus V squared over R. So that's how you feel when you're at the top. When you're at the bottom, it's going to feel differently. What is that? So let's look at the bottom situation. This is you at the bottom situation. Again, you have the weight, and weight doesn't change, right? Weight just equal to mass times square root the G. Do you feel differently? If you feel differently, the end of the bottom, which is this one here, this normal force, should be different. And you look at the picture, it looks like longer. Why would that look like longer? If I make the free body diagram on this situation, then you will find out. Okay, we look at the bottom. It has the weight going this direction. What is the normal force? The normal force going to the top. And this is the bottom one. What about the centripetal force? Well, centripetal force always over to the center of the circle, so it go up instead of going down. So if we use the bottom part to draw the free body diagram, and we now this time I'm going to use toward to the top because I'm just follow the centripetal force direction, and this summation of the net force will be equal to my m times a acceleration. And that's the centripetal force. This is F of cent. And what's the net force? Well, the net force going up to be the positive, so the BOT minus W equal to mv squared over R. How I feel is the M button. So my M but equal to W plus mv squared over R. And again, W is M times G. You can factor out the M. There will be G plus V squared over R. Now you compare these two values, this value and this value. Which one is larger? One is positive, one is negative, one is plus, one is minus. So obviously, when you are at the bottom, you feel more, as opposed to you are at the top. When you're at the top, you feel your heart is going to fly away, and that was due to the acceleration actually, and that will be the situation to tell you why you feel differently. And this is the way that we can show you. Okay, the last situation that we have in here is the merry-go-round. The situation is different from the previous one. This one go horizontally, so the gravitation is going downwards against to the ground, instead of going along the person. So now you're given with the situation. So you're given the mass of the child. So this one is 19 kilogram, and go around, and it tells you it go around 1 revolution every 6 seconds. 6 seconds, you go 1 round. It tells you the R is 1.6 meter. And we want to find out what is the static friction force acting on the person. So that means if you are sitting on this kind of like a circular chair, and it's turning around, and you have a tendency you're going to fly away, right? But you didn't fly away was because there is a friction force. Okay, because you have a friction force against this wrong object. That's why you are not flying away. Then we want to find out what is that force is equal to. And that's what this problem is asking about. So to find this solution, you also need to draw a free body diagram. So what is the free body diagram looks like? Well, this person in here, we don't care about the way because the way is in the different direction. The direction that we care about is the direction along this circle, this radius. So this R. You are going to have a friction force. Otherwise, you're going to fly away. And then where is the friction force coming from? The friction force is coming from the centripetal force. So you have this friction force was because you have this F of the centripetal force, meaning the centripetal force is your friction force. Okay, now we want to find this friction force, and that is equal to our centripetal force. And what is the centripetal force? Is mass times the A sub centripetal acceleration, and we know this is the V squared over R. In this case, is the small r here. But what is the V? Well, you have to do some kind of calculation in order to find the V. How do we find the V? It tells you 1 round and 6 seconds. And our V is the distance over time. And how much time does it go for a 1 round? It's 6 seconds, but how much distance did it go for 1 round? The one round is equal to 2 pi times the r. That's the distance if you are at the edge, and that would be this one here. And so you can figure out the velocity in this way, then you can solve this problem. Okay, so I'll give you 2 examples. I hope that you understand the idea of this and do some more homework that will help you to master this kind of problem.